Water is not a renewable resource, but it's one that is continuously reused and recycled. This cycle depends on the energy from the sun, but this cycle also moves energy around on the planet, acting almost like a heat pump. We take vapor from the oceans, moving into the atmosphere. That vapor is being moved over land where condensation happens, and the water is then returned to the oceans, and along with that, the energy. On a much smaller and perhaps more so relevant scale, we've previously looked how precipitation and irrigation may be partitioned into infiltration, runoff, evaporation from soil surfaces, and transpiration as water moving through the plant system. We may use this information to derive what is called a water balance for the root zone. And in order to do this, we need to also include capillary rise as an addition of water to the root zone, as well as drainage, which is water that is percolating past the influence of the root zone where it can no longer be accessed by plants. We may then write a water balance, much like we would write a balance sheet or an income and expenditure sheet, where we have precipitation, irrigation, and capillary rise as income, and we have transpiration, evaporation, runoff, and drainage as expenditures. The balance between the two equals to S and V, where V is the water that is being stored in biological tissues, and S is the soil moisture storage. And here we can look at just a simple example to say that, well, even if the income is zero, so for example on the Palouse in August when it's not been raining for a while and there's no irrigation, we can still have expenditures in terms of transpiration from plants if we deplete the soil moisture storage. Over the long term, the difference between precipitation and evapotranspiration is the water available for ecosystems, where evaporation occurs on surfaces of open water or soil, and transpiration is the removal of water by plants. But for evapotranspiration, it needs energy, and needs quite a bit of energy. Here's a graph that shows how temperature increases are related to heat inputs for water. And you may remember this from an earlier discussion where it takes a lot of energy to break the bond that forms between water molecules. And especially the bond as we go from liquid to the vapor phase requires lots of energy input. And we call this energy the latent heat of vaporization or the latent heat of evapotranspiration. Let's do a little example to figure out how much energy exactly this is. So the latent heat of evapotranspiration or of vaporization is 2,450 kilojoules per kilogram of water. Knowing that the density of water is 1,000 kilograms per cubic meter, and rearranging the volume of 1 cubic meter slightly to express this in terms of a surface area of a square meter times the height of a millimeter, we can calculate that it takes 2,450 kilojoules of energy to evaporate the depth of 1 millimeter of water from a 1 meter squared surface, which equals 0.1 or 1/10 of a liter of water. So the 2,450 kilojoules of energy that you would need to evaporate that 1 millimeter or 1/10 of a liter of water from a 1 meter squared surface equals the energy contained in 1.3 liters of your favorite sugary beverage, just for comparison. Of course, the energy is coming from the sun, and we can measure on the edges of our atmosphere that we receive about 1,370 watts per meter squared, which is called the solar constant, but it's not really a constant. This 1,370 watts per meter squared may also be expressed in units of joules per meter squared per second. What we receive at the soil surface though, or the surface of a water body is the net radiation. And net radiation really is what is driving the evapotranspiration of water from these surfaces. And the net radiation is the difference between in and outgoing long wave radiation. But we may also look at this as the radiation that is available to heat the air, to heat the soil, and to evaporate water. So how much net radiation do we need to evaporate water? Or asked the other way around, how much water can we evaporate in a given day given some net radiation? For this, let's do a little example. Let's say that in North Idaho we receive about 175 watts per meter squared as net radiation, and that about 80% of that net radiation goes towards evaporating water either from surfaces, be it soil or water, or from plant leaves. So how much water can we expect to evaporate on a sunny day in Idaho? So we have 175 joules per meter squared per second. We convert that to joules per meter squared per day. We get to 15 megajoules per meter squared per day received in North Idaho. Now, if we divide that by our 2.45 megajoules per meter squared per millimeter, as per the previous example, we can calculate the depth, and also knowing that we have to multiply this by 0.8 to account for the 80% efficiency of converting that energy to an evaporation flux. And if we calculate this out, we get to 5 millimeters per day, meaning that from an open water surface with the area of 1 meter squared, we would expect to evaporate about 5 millimeters per day of water. And that, of course, is going to have implications for how we estimate how much water needs to be replenished through irrigation from crops grown on a sunny day. But we will deal with that in another video.